The last time we met, we had discussed the second law of thermodynamics. Raise this really quickly. We had given these three definitions, and these were not distinct definitions. They were each saying a different thing, but they're three ways of saying the same thing, which is a universal fact known as the second law of thermodynamics. All right? And so what I want to do briefly is I want to show you, demonstrate to you, that all three of these really are saying the same thing. And it might not necessarily be the easiest thing conceptually because they look like they're saying such different things. Okay? But remember where they came from. They came from intuitions that we had about the way the universe worked. We just maybe couldn't formalize them. Well, here they are, written down in formal physics language as universal laws. And so what we'll see, like I said, is that those intuitions aren't really separate intuitions at all, but it's one intuition about the universe, which turns out to be a true fact. Okay? So, here's how I'm going to demonstrate that these are all equivalent. And take a look, I'll flip back to them, but I'm going to use this top board. So, logically, to demonstrate that two statements are equal, what I have to show is that, so let me show you here in a second. If I have that A is the same as B, all right? A and B are two statements, and I want to show that they're logically the same. I've drawn this arrow, which basically means they're equal. What I mean is that A implies B. That's why there's an arrow going from A to B. This, a logician would say, this implication that A implies B tells us this, that if A is true, then B is true. Okay? Now, notice that it's a double-ended arrow, so I also am denoting that B implies A. So, if B is true, then A must be true. This is how you logically prove that two things are equivalent. It's not enough to just have it one way. If it was just like this, A implies B, then you wouldn't have an equivalence between the two. Or if it was just B implies A, all right? You have to have both. Let me give you a good example of where you would have a statement like this. You could say, all right, all tigers are striped cats, okay? So then, would it be all right to go backwards and say all striped cats are tigers? Well, no, not all striped cats are tigers. So just because all tigers are striped cats, it goes one way, doesn't mean that it comes back. That's the importance of this being logically equivalent both directions. This applies this, and this implies this. That's how we're going to prove this. And we're also going to look at the negation. So simply, this is a symbol in logic that means not, or the opposite of. And so what we're going to actually look at is something that mathematicians do all the time, which is see if something's true by trying to break it. Right? I think a statement's true. Can I break that statement? And what happens if I break that statement? And if I determine, oh, well, I break this A, it also breaks this B. And then if I break B, it also breaks A. Then that's another way of determining that those two things are equivalent. Okay? Again, going both ways, even for the negation case. So let's just get into this and you'll see what I mean. Let's first violate the Kelvin-Planck law. So I'm going to set up a scenario in which we have down here is a cold temperature and up here is a hot temperature. Okay, and this could be anything. These are just two items, hot and cold, that heat's flowing in between. All right, or we're going to set up. Then you'll notice that, well, we can put in engines. So I was calling these heat to work engines. Heat to work, or heat to work machines, I think. Okay, so this is what we did last time. I'm going to put in one of these machines, and I am going to draw in some amount of heat, QH, to denote that this is the incoming heat. The H just means I'm pulling it out of the top reservoir, okay? QH is what's coming in from this hot place, wherever my hotter source is. Coming into my machine, all right? Let's violate Kelvin Planck. Kelvin Planck is the one that said, my machine here cannot be 100% efficient. I can't just go ahead and pull all of this out in terms of work. All of QH, turn it into work. So let me denote this below the arrow. That means that this amount of work that I'm pulling out is equal to the same amount of work that I'm pulling in. Okay? Kelvin Planck says I can't do that. There's always going to be a little bit of heat leaking out or escaping down to the cold place, and so I can't get fully my QH in my work. But we're going to violate it. That means we're going to draw this as if that's what we're doing. Now, what I could do, okay, I violated one thing. I'm not going to violate anything else yet. I'm just going to see what happens. Let's put in a machine right here that goes backwards, work to heat. Okay, now what do we remember about work to heat? That can be 100% efficient, right? That's not violating anything. In the real world, we can have work to heat machines that are 100% efficient. So that means that I can take this work and I can, let's also pull a little bit of heat from the cold reservoir, okay? This is QC, that means that it's just the amount of heat, whatever amount we're getting from the cold reservoir. And that means that I can have 100% efficiency here and go up in the amount of the work plus the QC. Or I could rewrite it, because this was perfect, this was our violation, perfect machine, where work was equal to QH. I can have QH plus QC going back up, all right? And this machine we think is allowed, right? We haven't tried to cause a violation. All we've tried to violate is this. But notice, now what we've got is we've got one big machine. Imagine combining these two machines. We already don't know about the inner workings of what they do, right? This is just some black box. It could have a whole bunch of parts to it where things go around and energy flows here and there. So there's already complication here and complication here. Just stick them together. And we'll consider this as one big machine. Okay? And what do we have here? One big machine. Well, we've got a machine that inputs QH and outputs QH plus QC. That means that what we're doing is we're net resulting in just this arrow, this QC right here. You see that? It goes from the cold place, wherever the cold side of our machine is, to the hot place. But there's no work going in. Now, granted, inside here, in the inner workings, there's work. But like, once we've drawn the whole thing and we've considered all of this a machine, you may as well just rub it out, ignore it. It doesn't matter what's going on in there. But we're not feeding in work. So what we've just made is what Sean Noling here calls a magic refrigerator. Notice this is what a refrigerator does, right? It takes heat out of a cold place and pumps it into a hot place. The inside of the refrigerator is the cold place, and we're pumping heat out. That's what the refrigerator does. But refrigerators in the real world, they have to take work. We have to put work in. So here, we've just made a magic refrigerator, a machine that only allows heat to flow from cold to hot without putting any work in. Well, that is an exact violation of the Clausius statement. Look at this. For any cycle device, energy cannot flow via heat from a low temperature to a higher temperature without work input. That's what we just made. So notice that by violating this equation, this statement, we by default violated that statement. And so I'll also write this down here. This is an easy way to remember this one. Clausius is saying no magic refrigerators. So here's what we've got. We have intentionally violated Kelvin-Planck's statement, and what we got as a result was that we violated the Clausius statement. So this is like not A goes to not B, implies not B. Let's go the other way now, just to prove this full equivalency. Okay? I'm going to set up the same thing over here. We've got a cold place and a hot place up here. Let's start with violating the Clausius statement. All right, that's what I'm aiming to do here. I want to violate that law as phrased by Clausius. And what he said is we couldn't have a machine that magically pulled heat from a cold place to a hot place. If we're going to do that, we needed some work. That's what Clausius said. So let's start by setting that up. We'll set up a machine here that pulls some amount of heat, QC, up. And it goes in, oh sorry, this is just QC as well. It's the same amount, right? The heat's just streaming through like basically a pipe. This machine, whatever it does, basically is like a pipe. It just streams through. And there's no work coming in, okay? Now, what we'll do is if this already works by itself and it needs no work input, then if I were to give it work input, that's extra juice. It can output extra. So let's go ahead and pump some work into here, and whatever that amount is, that can also go up, right? I can pump work in and output it as heat. I know that that process is 100% efficient. Work can always be converted to heat. So now I'm just pumping extra juice through my machine, this machine that I've made that can do this. Now, where could I get this work from? Well, so we've already done our violation. We violated Clausius. Let's put another machine in. We're not trying to violate anything, but this time we'll put a work to heat machine in. Okay, where it's going to convert work into heat. Now notice, and this is where, I guess this could be heat. Let's call it Q high. You'll see that in a second. The point is that this is an energy flow. So whatever energy flow we put in here, it can suck it up, okay? And we know that work can be converted 100% into heat, all right? So this could be, we could draw from here. This is why I called it QH, because we can draw heat from the hot reservoir into our machine, which can just pipe it through, like a pipe, 100%. That's fine. Okay? But this has to be, this is work that's coming out, remember? I'll put back the W. So, what we've created in doing this is inadvertently, without wanting to, but we've created a system where the same amount of heat comes in, goes out, and goes out in addition to this. And so this thing is 100% efficient. We're converting, sorry, this is a heat to work machine. That's what's wrong with this. I was like, that's not making sense. This is a heat to work machine because this is heat coming in here and we're outputting work, and this QH just happens to be the amount of work. But it's 100% efficient. And that was it. We could freely choose to put that in. Once we violated the Clausius statement, we can put in any amount of work we want and see what happens. So you get that if you if you put in a violation of the Clausius, you automatically get a violation of the Kelvin-Planck. Okay. So now you can say the full story. We've proven that if we violated Kelvin-Planck's statement, we violated the Clausius statement. So the implication goes one way. If we violate Clausius, we violate Kelvin-Planck. That means the implication goes the other way. That means that we've proven that not A implies not B, all right? And not B implies not A. This is equivalency, all right? And we might denote it as just A equals B, okay? Just for simple ways of notating it. These two statements of the second law are identical. And the last one that we want to talk about is simply the modern physics statement that entropy increases. Well, look at the Clausius thing for a second. Look at this picture. We could look at either, but this one where we've got drawn a big box, we've got heat flowing on its own with no work, just spontaneously able to flow from the cold side to the hot side. Well, what does that mean? The hot side has more entropy. The cold side has less entropy. So we are taking energy in a lower entropy form and bringing it to entropy, this with a higher entropy form. So what we're doing is we're lowering the entropy up here because we're bringing in that organized energy, right? This was random, and this was organized. We can phrase it like that, organized energy and energy that's more random. Well, if we're drawing this energy from here to here, then we're actually de-randomizing this. As we bring more and more, this gets more and more organized. And so the entropy is actually decreasing, just spontaneously. We don't have to put in work for that to be the case. And so the Clausius statement, we violate that, then we've also violated the moderate statement. And the equivalency can be shown the other way as well. So we have three statements that are all equivalent. One law. There's only one second law of thermodynamics. This isn't a whole bunch of laws. This is one law. Just three ways of phrasing it. All right, thanks guys.